pick up. So I just want to remind us what we did last time. Saw something pretty confusing. So I'm going to assume p mu, or pi mu if you will, is proportional to 1. And so both the Bayesian and frequentist intervals. Now, I'm going to mention this term in a second. Both of these, I'm kind of using synonyms for things that might be on the board. Bayesian and frequentist intervals are x bar minus 1.96 sigma over root n to x bar plus 1.96 sigma over root n. And how you think about these two intervals is a little bit different. So where you're getting this interval from is this statement. I'm going to say, myself just a little bit around 1.96, is that mu is between both these two things. So this is a probability statement, and this is equal to 0.95. And both Bayesians and non-Bayesians, I'm calling them frequentist because there's a property that we're invoking. So the coverage property, coverage is a frequentist property. So I would say that confidence intervals are strictly frequentist intervals. And some of them are exact intervals that they actually cover with that probability, and some of them get there as n gets bigger and bigger. This interval is exact. So this has not asymptotic frequentist properties, but just frequentist coverage properties. And the frequentist is making statements about this thing. This is what's random. That's random from a classical perspective. I would agree that most frequentists coincide with the classicists that think that the data is a random thing, and I agree, the data is random. The Bayesian takes advantage of that by turning their probability distributions of the x bar, or some transformation of it, and turns it into a likelihood. It starts conditioning on that data. So they have a conditional interval. It's a little bit different. So the classicists are usually treating that as a random thing, classical just being old. So this was the school of thought early, modeling the randomness in data that we've observed. And even getting there took a long time for people to just accept. They thought, no, you should just be able to take better measurements. And those of you that have been doing science for a minute know that you can never get rid of the inherent uncertainty, no matter how you think about it. So it's always going to be there. The way you think about it might cause you to gripe with other people that think about it differently. But Bayesians use the randomness to induce their likelihood. And the Bayesian is calling that random. I'll say this is random for Bayesians. An engineer says, whatever. Just do it. So I don't care. I mean, for me, I kind of like you get kind of a similar probability statement, but you're just thinking about something different. And there's a nice inherent symmetry in this problem. It's making that happen. So I would say the Bayesian's interval also covers at 95%. So this is an exact probability statement, and their intervals will also cover. So the Bayesian in this example can be a really good frequentist. And they have a really good interpretation about saying this is where I believe mu is. And that was the thing that my previous instructors would have discounted lots of points for if you said something like that. Personally, I hope you say both in this example, but that's not always true. So I want to look at another example where answers that are induced by thinking about coverage might be different from belief sets, and we'll decide which one we like better. So again, I'm hoping you just convey good answers to people and tell them what the properties of those answers are. But I also hope you have ways of thinking about this stuff so you can construct these answers. Exactly polarizing everybody to think about it exactly how you think about it is probably not going to happen. So I recommend having multiple ways to think about things. Okay, let's just go back to this example. Xi, or write it over here and give myself some room. Xi's can be one of two values, theta plus 1 or theta minus 1. And theta here is an element between negative infinity and infinity. So it can be any real number. Just shift this thing around. This is going to happen with a probability. We'll discuss this a little bit later. I'm going to just say that it's 1/2 and you get to know this. The only thing you're going to try to learn is what theta is. So this happens with probability. 1 minus p. That's actually. So this is a binomial problem. The way that it's phrased, but you're not quite sure what you get to observe. So this is a little bit different. We're not going to encode them as ones and zeros. We're going to encode them with a shift in here. So just real quickly, if theta were 5, all we're going to get is xi could be either 6 or 4. With prob half and 1/2. So if I told you everything about this problem, if I told you what theta was, then those are the numbers that you would observe. Now if I take this away from you, I don't let you see this, and I just tell you this, you're not sure what numbers you're going to observe. Once you see the first realization, it tells you a lot, but it doesn't tell you everything. So let me just ask you a question. Let's say I ended up getting, I take this away, I don't let you see this. Let's say my xi was equal to a 6. What do you think theta is? Just make sure we're thinking about this problem. This requires thought. 5 or 7. So you would say it's either 5 or 7, I already know that. So if you got a 6 again, that wouldn't help you to resolve that question. But if you ended up seeing a 4 on the next one, you would know which one it is. You know theta has to be 5. So let's play this game a little bit more. So I think what you did is you took that number and you added 1 and you subtracted 1 to it. So we were looking at this relationship that theta xi is an element of 1 or 2 things. Theta plus 1 and theta minus 1. That's already written on the board. That's pretty easy. 2 possibilities. So I could rewrite this. This is called pivoting. So just rewriting the expression in terms of theta. Xi minus 1 and xi plus 1. Subtract off 1. You can do that. 2 very easy linear solves. And so I know these things. This is important. Question. If I didn't know the problem setup, I couldn't make this statement. So hopefully you understand something about the problem setup. Most scientists I work with, even though this probably isn't a real problem at all, have some understanding of what the realizations are. So I would say in a real scientific problem, you probably have some understanding of what theta can even be in the first place. And we're going to remove that knowledge. This is just an artificial problem. Okay, here is a 75% confidence set. I'll write it down in a second. I'm going to say this is going to be this new letter C, it stands for confidence. It's going to be a function of 2 realizations, x1 and x2. So I'm going to let you observe 2 data points. Again, I'd probably tell somebody just go out there and say it a couple times. So I'm pretty sure we could probably tell ourselves what a 75% confidence set is real quickly. But let me just ask Dylan one more time. So you said it's either going to be a 5 or it's going to be a, what were my numbers? 5 or 7. I did say 6. So I messed that up. So, I guess that's right. So 5 or a 7, we'd say something like that. What's the probability you get that right? If you just guessed it 1. What's that? 1 out of 3. 1 out of 3. There's 2 possibilities. I'm going to just change my number again. So I'm going to say, well, we'll stick with this. Theta is 5. Just remember that. So this right here could either be a 7 or a 6 or a 4. So what are the probabilities that those things even happen? It's a half. It's right here. So this happens with probability 1/2. That happens with probability 1/2. Those numbers are there. So there's a half chance that this thing even happens in the first place. Right? Now you're going to make a guess on what the actual theta value is. What's the probability you get that? A half. So there's no third, it's just 1/2. So if you're going to give somebody an answer, you're going to cover that truth with probability 1/2. But there's another possibility in here. So I want to break down these 2 possibilities. So I'm going to say, I'm going to give you back x1 minus 1 if x1 is equal to x2. So they're the same draws, and I didn't learn anything new on the second draw. And I'm going to hand you that answer back, pretty arbitrarily. I'm going to give you one of these, but I don't get to say both of them. If I told you both, I would already 100% cover right there. And I would agree you probably should, but I want you to just think about what these numbers mean. So this is just an exercise. If x1 is not equal to x2, what should you tell people? How would you report the answer back? You would just report back 100%. I'm 100% right, and you march on your way? Cool, wow, Chris is really selfish. So you won't even share the answer with the person and tell you how to compute it? So somebody comes to you for help? I know how to do this. Yeah. So what would you compute for? You compute x1 and x2?
Or theta.
Or theta. So tell me what theta should be. The average. I like that. So x1 plus x2. There's a lot of ways that you could phrase this. But that's going to be theta minus 1 plus theta plus 1. I don't know which order they came in. But I know they're 2 different things. This is not equal, so these are different. These are the same. So divided by 2, this is 2 theta divided by 2. So that's what Chris means when he says, I'll just give you the answer. I'll tell you exactly what theta happens. So this has got 100% coverage. This has 50% coverage. I would agree, I would probably tell the person about the other answer, but we're trying to think of a process on how to even paradigm for even trying to tell people what the answer might look like. So, how often does this happen? How often do they match? 50% of the time. And 50% of the time, you don't match. average. Let's just make sure we understand that this happens 50% of the time. What's the probability I'm going to get one of these two numbers? 100. Let's say it's that one. What's the probability that I match it on the next draw? 50%. Now what happened here? Maybe I got this one, and I condition on I saw something on the first draw that happens, the probability you match it is 50%. Anyway, you're down the first one, you can marginalize both of those things. It's a half anyway. So this is half the time, this is half the time. Two different possibilities. This covers 50% of the time, this covers all the time. 50% times 50%. Just write this down. 50% times 1/2. So that's the 1/2 here. Plus 100% times 1/2. 75%. So I'm just giving you this as a process. This is a 75% confidence set. So here's what the answer is. So when I talk about what is a confidence set or a confidence interval, it's a process that you're imagining. So, Bayesians believe something about what they think the parameter is, and they model that either with the ignorance or knowledge, whatever you want to call that stuff. So, subjective information and frequentists that are using confidence intervals are imagining things about the future that didn't actually happen. So, Bayesian conditions, and they've got this extra gadget in their machinery to kind of weight how we believe in different things. I think the amazing trick is to think that the Bayesians were the nutty ones. You know? What do you think? Am I trenching into dark territory?
Let's see what we're doing.
Yeah, exactly. I think I'm setting up a debate, right? So this is Deborah's written a paper on this exact problem. So she asked me if I wanted to author on the paper, and I said no, I haven't touched this. So, you know, I don't want to get into arguments all the time. So that's what I don't love about philosophy is nobody ever goes, you know what, everybody's right here. So I appreciate the engineers. This might not be a great answer, I would say. I think there's a lot of ways to come up with these different answers right here. Anyway, this is a 75% confidence set, so it's just a statement about the process. So I write down this process. So I compute this, I draw two samples from this process right here, I compute this, and if I give this right here, I tell the person I'm 75% confident. And if I give this answer right here, I tell them I'm 75% confident. So that's the big trick here, is why would I report that? That is an answer, and that does get described by the paradigm. So I would agree this is a terrible answer. But I'm 75% confident. If I were reporting this right here, I'd probably want to say I'm 50%. If I were reporting this, I'd probably want to say that I'm 100%. So there's a paper on the webpage, and it says, could Jeffries, Fisher, and Naiman have agreed? And this part of the paper is about this problem. And they propose a solution. And they say there's something called the conditional frequentist. And they described it, and I had never heard about that when I was going through grad school. What the conditional frequentist is. But the conditional frequentist is able to condition on an ancillary statistic in a particular way. There's no paradigm for exactly telling you how to do that. But if I could condition on these two statements with a sufficient statistic, i.e. I look at x1 minus x2, and just look at the absolute value. Is this 0 or is it 2? So that's ancillary information. And those of you that have taken inference class knows what an ancillary statistic is. I'm not going to test on it here. But on its own, that difference doesn't have any information about theta, which is telling you about the spread, but it's telling you which case you're in. And so frequentists usually do not condition on the data. Usually that's Bayesian. So Bayesian is going to condition on the sufficient statistics and the ancillary statistics and the complete statistics if they're complete and everything. They're going to condition on the data set. Everything about it is going to come through that minimal sufficient statistic effectively, but you're going to get all the ancillary information as well. So it's conditioning for you. Point being is that you need to be able to condition and tell you what cases you are, and you have to do it on the data. And I think people tried to pursue this school of thought back in the 70s, and they couldn't really come up with how do you pick the right sufficient statistic. Because on its own, it doesn't tell you anything about it. I think it's just a mental game. It's very hard to do. Every problem is its own unique problem. So I would say this is a terrible answer to report this, but it's just to highlight what confidence really is. What is this confidence statement? It's a statement about the process, and you're always reporting back 75%. Now, if you call yourself a frequentist or a classicist and said, I understand what this problem is about, but I would never report that, I would report back either 50% and I would tell them the other 50% measure, or I'd tell them 100%, depending on those two cases. And I would go, that's great, you're a good person. And I would ask you, what's your paradigm for doing that? And you'd say, I don't know, I just thought about it. And so that's not something you can exactly write a paper about, or tell people how to use in the future. So now let's look at a Bayesian solution and watch them just automatically condition. Bless you. This is my favorite thing about Bayesian analysis. Bless you again. I got it too. This is my favorite thing about Bayesian analysis is the conditioning on data, conditioning on what you've actually observed. It's not the prior, it's the likelihood, what likelihoods do. Once we get into joint inference, we're almost there. I'll tell you about what likelihoods do with joint parameter sets that I really like. So, but this is just a one-dimensional example because we're just learning this parameter data. So, for a Bayesian, you need to compute pi theta given x1 and x2. That's the only thing that Bayesians do. That's what makes you a Bayesian. As soon as I write that down, a statement like that I'm conditioning on the data, and I'm going to come up with a probability statement on what theta is, and I can probably call this PR right here because it's a probability and not a density or something. So I'll be more specific and I'll use PR. That one always bothered me in textbooks. Why ask for that one? PR is easy enough to write. So Bayesian wants this thing. How did we get it? Always the same thing. x1, x2 times pi theta. Those are the two ingredients into a Bayesian analysis every single time. So you're thinking about likelihood and you're thinking about probability. How do we get likelihood? We think about the process. So x1 is equal to theta plus 1, theta minus 1. This happens with probability of half, and this happens with probability of half. So half of both of those. So somebody help me out. What's this? And I bet a lot of you are already thinking and ready to just launch answers to the prior. You don't need to see the data to look at it. You don't need to actually, I mean, if you knew what my coins were that I pulled out and whatever this trick coin was, maybe you'd supply some information on this. Might be thinking, that stuff that never picks big things. I always say it's silly. So I don't even know what numbers I'm saying are so big. So my betas are never free, so walking down my beta would be hard. So, but you probably have an answer as to which theta and what. Told me you're ready to go, right? Which theta, which pi theta and what? Too much on the spot. I don't. What? So, Dylan. Beta. So, data. Oh, yeah. Either one. Data numbers. Think about it. Data form. What's that?
I said theta.
Theta the mean. What?
Such thing as a discrete form.
I mean, if you can imagine a continuous uniform, it's easier for me to imagine a discrete uniform. Where would you place the masses?
Well, I got confused because I told me
It doesn't.
yeah, we just do
Proportional to 1, so 2 on that. So let's just start writing down these answers. So just as we're thinking about this, the second ingredient, pi theta, we've got maybe proportional to 1. We've got theta, alpha beta. We've got discrete, but we changed that answer, theta.
Ideally, we get the, we insert our first step, like, there would be 2 possible values for theta. I think ideally that is really.
I'm going to say that's off limits for now. I'll discuss glancing at your data later in the class, but this is a prior distribution, so you don't get to see it yet. All you get to observe is my process. And the 5 I put up there was just for illustration purposes, because I can't add numbers to make numbers.
I just have a question, like, if you know if it isn't an integer,
Don't.
you know, okay, so it could be anything, it could be something continuous.
Yeah, theta is between. I think I wrote that at the top of the board, but I'll write it down one more time. Theta can be anything. So that's cool. If you guys did say, I'm going to put point masses down on the integers, if it's a non-integer, you will never hit it. Because you're going to put 0 probability on that. And it's an interesting question of what would happen in the Bayesian model. And it would push right against the closest answer you gave possibility. Which will happen. You'll see this in a future problem. So it could be anything. So Colby kind of walked back the thing and said proportional to 1. Anybody else? Let's just look at this answer. Is this a good answer? Beta?
Between 0 and 1.
That's right. So this is going to assume theta is an element of 0 and 1. And so if theta was between those, then I would think you have some good chance of getting the answer there. So off of the 2 data points, I can't tell. It depends on how you pick that alpha and beta parameter. So you might heavily bias things. Keep in mind, 2 data points isn't a ton. But this has all kinds of problems. So this is the first thing I ever look at, is what's the support. And this doesn't match this. And if they don't match each other, then that's not a great prior suggestion. I would call those dogmatic priors. I'm going to force my answer to be between 0 and 1. And no amount of data can change my mind. And if you're like that, you're in the wrong class. So political science is down the way. So that's a different field. Anybody else?
I was going to argue for proportional,
Why?
because you told us that if it's an location, then we should use proportional to 1.
And that's how you would answer. You would say to somebody, "Well, stop and my teacher told me that if it's like this, then I would have to." By the way, Scotland never told you you had to do anything. So let's get that part right.
You use like, weight or something,
They can only be 2 values. Why can it? But theta can no. That's right. You know that, but you don't know what theta can be. So once you see some data, you know it's going to be 1 of 2 data values. But before you sample from anything, you don't know anything about it. So I kind of understand David's thing to be a data point. There's something called a minimal training set. And I would say that's a step in that direction. How much data can you use and why? And there are attempts to get that right. And I'm not super opposed to that, but we're not doing that.
I was thinking because when you have theta belongs to the xi minus 1, then xi plus 1.
No, the thing that lives here
theta going to be like a discrete value because if xi is discrete, theta belongs to xi. It's going to be value at gamma.
You're stuck, aren't you? You can still that. Again, that other thing, you haven't seen the data yet. You're about to do something that's a major violation of likelihood. And there are repercussions. Keep in mind, if you use a normal prior centered at x bar, for a normal analysis, you would say you're really certain about where the true parameter is. It's not giving you the same posterior back, it's concentrating that normal and stacking mass. So your measures on how uncertain you are overly optimistic.
Will it pick like some conjugate prior that you can like tweak until it's basically proportional?
So we probably have to scare the likelihood to do that. We don't actually know what that would be in this case.
And then, if you had a different scenario where like you knew that data was like between some continuous range or it could be a discrete value outside of it, what do you pick for your prior?
We don't want to answer this question first.
Well, I was just thinking.
Let's come up with different problems. I would pick something in that interval and come up with a prior in that interval without any context or information about the problem. I wouldn't know how to build that function. But this problem I told you a ton about is a shift parameter. And so, since the nature of that problem is a location, so this thing is just shifting this around 1 unit to the right, theta shifts, these down points shift. And so that's just a location parameter. So I might want to be location invariant. So not because Scotland told me, it's because I want a location invariant prior. This is the location invariant problem. So I don't want to inject information about the location. That would be a good enough reason for me. So, but it's not because I said it. It's because that's what it is. Different. That would be the reason I would give. So I wouldn't trust you if you said, well, I don't know my teachers. You know who I would go talk to? Teachers. You're out. Teachers in. So we're going to all be the expert on one of these things and have our reasons. And we can say it pretty confidently. We can also do sensitivity analysis, wiggle around the prior, see how much difference it makes, things like that. But let's do the second part. And maybe we can start to recognize what a conjugate prior even could look like here. But we can't even address that question until we stare at the likelihood. So what is the likelihood look like? Usually I look at this first. So what does it look like? Here, I'll help you out. If you'd like, this is not a probability statement once I turn it into a statement about theta. So I'm going to give myself a heads up that this isn't the sampling distribution. This is x1, conditional on x1, x2, proportional to that. That's the process. Every single time I write down my sampling distribution, if I can do that, then I've already got down on paper the likelihood. All I have to do is change the way I think about it and think of this as a function of theta. That's why I prefer this notation. It's just my preference. Lets me know I'm doing something. Sometimes I have things that anchor me down and I always see them the same way. If you want to change that into something that looks more like Bayesian theorem, I can adjust. You just have to tell me. Don't write it with the same notation of the sampling distribution, even though there's a lot of papers. So what's this? Anybody want to come up and wow everybody? Dylan's ready. Awesome.
I mean, those constant. But this is just, they should be independent. I should be able to say this is the probability of x I given theta squared. And we just need to know about it, right?
Yeah, so write it down. My computer won't understand that
So
formula.
the probability of x I is going to be
numbers. So just going back to the example, if data were 5, I'm either seeing a 6 and a 4 or 6 and a 6 and a 4 and a 4.
So it's 1/2 to kind of like 2 or 3.
That's something happens in the form, isn't it? It's amazing. So you're raising it to the 6 or the 4? That's what those numbers
It's
are.
xi minus theta plus 1, xi minus theta minus 1.
Normally we have x1 minus x.
Those are like 6s and 4s.
Yeah, so we have to do xi
Minus theta.
minus theta plus 1, something like this, plus theta plus 1 theta squared. And then we can combine it with halves. So things end up canceling out.
And then what do you get?
You get 1/2 to the let's see that side cancel out.
I think it's xi minus 2. Really good.
Something. You're still on square.
Anybody else want to know? That's the answer.
I'm trying to.
Yeah, I'm sure it's all going to confuse you. Hit the chair right there. Anybody else want to come up? You have time to think about his answer. Michael, let's do it. No? Not today. Chris, you had lots of insights.
I think that's what I got minus 6 squared.
I love it, man. Oh, don't erase his answer.
So the 2 p's are 1/2, they're the same place. And then the 1 is, if I do xi minus theta minus 1, it's like I'm subtracting that first probability, that first possibility. And then the second, I'll do it from here, so minus theta minus 1. Plus 1.
So let me just get this right. If your xi doesn't pair well, so these are just the same numbers, what is this?
This was originally minus theta plus 1, and then I distributed the minus.
Aren't these normally indicators sitting up here?
I think we have a battery.
Aren't they just indicators that we put up there?
Yeah.
So if this 6 and this 4 was green and blue, I could handle this problem, right? So they're just counting things. Yeah, these are pretty funny ways to write that. So do what with some indicators they indicate. I think you guys are on a path that could get us to the right. But I remember Bernie Leaks always being, he always wrote it like this. P to the, I'm going to call it yi, just because I have xi. 1 minus p to the 1 minus yi, but yi had to be a 0 or 1. So usually what I might do is I might say p to the indicator function, the yi is equal to element 1, whatever I want to call that, and 1 minus p to the indicator. I'll say indicator yi is equal to element 2. So they're just counting things. Hi, Chow agrees. She's like, heck yeah, that's what Bernoulli looks like. I don't know about all this other stuff with these free parameters rolling around. There's no constraints on this. This number, if I drag this around, this theta, I could make this, remember this is going to be a function of theta, I can turn this into things that are not indicators. I can turn this into a million, negative a million, a zillion, any number of them. and there are constraints in a Bernoulli that say, no, this is a 1 or a 0 out there. And that's the only thing that distribution can take on. Make sense? So that's at least, I kind of like the learning lesson. But let's finish the answer with that. Somebody help Chris out, please. There's bigger ones.
Like,
Why the square? Okay, I got you. You guys think of this answer. Let's simplify. I like your answer. Let's simplify this a little bit. So this is either a 1, or that's 1, or a 0, or a 0. So I think that the notation here, just to be really clear, this is like my yi xi is equal to theta minus 1. And this one right here is delta xi is equal to theta plus 1. And that started to look a lot like the things on the board. And it is hard once you get to the board and you start writing things down. Totally different. Okay, so this is either a 1 or a 0, so good, at least that kind of feels good. So what's this number in here? That's either a 1 or a 0, that's a 1 or a 0, but there's kind of a connection between this. If that's a 1, that's a 0, if that's a 0, that's a 1. So what's this number always? 1/2 raised to the 2. This expression is always 1/4. Always. Anytime you compute that, that number is 1/4. Over all the years I've done this, 18 years in a row, nobody has written this number. This has been fun. So just like everything else. And then if I had pressed on this, I would have messed it up too. I read the answer before I knew the problem. What's the problem here? So I'm going to give you a hint. There's no thetas in here. And I'm going to make a statement. I know that there are counterexamples of really bizarre problems where, and I've seen them, and I usually end up thinking you wrote down the way to think about the sampling distribution. If theta doesn't appear in your likelihood, you probably messed up.
was I supposed to put a xi in the delta function, like xi minus?
Yeah, I think so. I would have put that in there. So I'm writing it like this, xi is equal to theta. But a lot of times, I think what you're writing is xi down here. You see people sometimes do that, and they match those two arguments. And if they match, it's a 1, and if they don't match, it's a 0. So I think you're writing the right thing. I would have written my delta functions like this. And put the xi in there, but it's a function of them. So I took your notation to be that. So I'll write this back down. So a little bit clearer. These are just the 2 data points, x1 and x2. We're not getting anything extra out of that. And this is going to be proportional to. We make this look real fancy. This is going to be 1/2 delta xi minus or equal to theta plus 1 times 1/2 delta xi equal to theta minus 1. We just did a lot of work. That's equal to 1/4, and this is not correct. And the first inkling we have that it's not correct is you got the things over there. I was wondering how long I could put that right in the middle of the board. If you're not encoding that information, you don't have that. just want us to stare right here, because we are tripping over it.
Okay, so I think, it's great, like, we do a product from ice, just one to n,
No, it's just 2, and it's 2.
in the, product, we show the, whatever 2 times indicator function set is, xi plus 1, xi minus 1, and then the indicator function is that.
Okay. This is what Nathan said. We need to encode that indicator function. It's telling us a constraint on the parameter. I agree, it can be 1 of 2 values. And this doesn't say this shit. So it's just not in there. So anytime your parameter is on the boundary of the space and defining that boundary of the space, you need to encode an indicator function. So this is not correct. This is correct. I'm going to just write it down like this. Likelihood theta is x1, x2. It's going to be proportional to I goes from 1 to 2. Probability of xi, given theta. Same thing as always. This is equal to, I'm going to call this 2 right here. 2. This is our friend, 1/2. That part's always a half. That's this thing right in here. You can write it all fancy if you'd like. It's still a half times. And that's just that stuff right there. That xi is an element of theta plus 1. Theta minus 1. That's it. Put those in sets. Let you know that's not an interval, that's discrete. I can do that. This thing is proportional to, this part doesn't help us at all. So we spend all our time thinking about the normalizing constant. I don't mean to make fun, I do find it amusing because I've seen this hundreds of times, you know? So, and it does seem like that. I probably would have fumbled around with that, and then this is the inside right here. The likelihood is just this part. So it's just going to be, I'm going to rewrite it. Theta is an element of x I minus 1, xi plus 1. And I'll just take this product of these two things. So it's just the product of these two indicators. So the likelihood is an indicator. That's kind of. So don't forget all the information in your problem. That's an easy way to mess it up. This is a really interesting way to kind of go about this problem. I would say if you didn't know what the keys were, that part you're playing around with will tell you about the keys. And if I did pick different probabilities for the things and not a half and a half, that part wouldn't matter. So, something to keep in mind. The half in there made it so that this part didn't matter at all. Question is what does this function look like? That's the likelihood. And if I multiply it by 1, this would be proportional to my posterior. So I want you to just kind of play around with this indicator and think about it, and we're going to draw it on the board. In the case where the xi's are the same, this is going to be 2 indicators. And you'll know where those 2 points sit. And if the 2 xi's are different, this will be 1 indicator. And you know where that thing is going to sit. The likelihood has all the information. That's what I would argue. The Bayesian takes it one step further, and they turn that likelihood with either 2 indicators that are the same heights, or 1 indicator equal probability function. So let's go back, finish that out, and just remind ourselves what confidence intervals are again, what they are not, and what Bayesian intervals are. The nice thing about the Bayesian interval is it will cover, and have a nice coverage property as well. That's kind of cool. We'll come back, draw the different cases. We just have a couple cases to look at here. And then we're going to move on, I think, to the Poisson examples. We're going to get through that, and then we're going to get through MCMC. So just a reminder, review tomorrow at 6:30. We're going to start up. It's going to be in seats 207. I'm going to send that out on Slack so that you guys can remember it. So we'll just write this down, review. 6:30 p.m. in seats. And I'm pretty sure this is right. 207 is what I wrote down on my hand, but I have a confirmation email. I'll post it to Slack, so just be aware you should look that up. Does anybody know where seats is? What's that? Through that wall right there. You can walk around, you can walk through the attic quad. It's right up there, I think. So we're pretty close. So if you get lost and you show up, look for a familiar face, and they're probably in the same boat. Thanks, you guys.